Hey everyone, and welcome. Today we're diving into the world of transmission lines. Now, you probably think you have a pretty good handle on how a simple electrical circuit works, but what happens when that circuit gets really, really long? Well, as we're about to see, the basic rules you learned in class start to break down in some pretty fascinating ways.
So, what are we actually talking about here? Physically, a transmission line is just any structure that's designed to guide an electromagnetic wave from point A to point B. And you see these things every single day. The coaxial cable bringing you TV or internet, those old-school twin lead wires for an antenna, or even the microscopic parallel plates connecting components inside a microchip. Their job is simple: get the signal where it needs to go.
To really get why we need a whole special theory for these lines, let's just step back to basics for a second. We're going to start in that comfortable, familiar world of low-frequency electronics, the stuff you probably covered in your very first circuits class.
Okay, picture a standard RLC circuit. When you turn it on, a current flows. And what are you taught to assume? You're taught that the current flowing through the resistor is the exact same, at the exact same instant as the current flowing through the inductor and the capacitor. And for small circuits on a lab bench, you know what? That assumption works beautifully.
But let's blow this up. Let's change the scale. Imagine that same circuit, but we stretch the wires out so they're a kilometer long. Now, does it still make sense that the current at the beginning of the wire is instantly the same as the current at the end? No way. A signal can't teleport across a kilometer. It has to travel. And this is the exact point where our simple model completely falls apart.
So, what's the missing piece here? Well, the crucial idea is that signals don't travel instantaneously. They have a finite speed, a speed limit. And this brings us to one of the most important concepts in all of this: the signal's wavelength.
To really let that sink in, think about the Andromeda galaxy. The light you see from it when you look up at the night sky, that light actually left 2.5 million years ago. It took all that time to reach you. Signals aren't instant. And just like the light from a distant star, the electrical signal you send down a wire takes time to get from one end to the other.
And this brings us to the absolute core rule of transmission lines. It's all about a comparison. You have to compare the physical length of your circuit, let's call it L, to the wavelength of the signal you're sending, which we call lambda. If your circuit is tiny, much smaller than the wavelength, then guess what? Standard circuit theory works just fine. But the moment that circuit's length starts to become a noticeable fraction of the wavelength, the old rules are out the window.
Let's put some numbers on this, because the difference is just staggering. Take the 50 Hz signal coming out of your wall outlet. Its wavelength is a massive 6,000 kilometers. So yeah, your 1 meter long lamp cord is completely insignificant compared to that. But now, let's jump to a 100 gigahertz signal, the kind used in modern communications. The wavelength there is just 3 millimeters. Suddenly, even the tiniest little trace on a computer chip is electrically long, and our old assumptions fail.
So, we obviously need a new model. Since we know the voltage and current are changing all along the circuit, we can't think of things like resistance or capacitance as single, lumped components anymore. We have to start seeing them as being spread out or distributed along the entire length of the line.
This new model is built on 4 fundamental parameters. You'll recognize the names: resistance, inductance, capacitance, and conductance. But here's the crucial difference. They are all defined per unit length. So now we're talking about resistance per meter, inductance per meter, and so on. We're not thinking about a single resistor anymore, but a property that exists continuously along the entire line.
The way we visualize this is by imagining the line as an infinite chain of tiny segments. Each little piece, we'll call it delta Z, has its own little chunk of resistance, inductance, capacitance, and conductance. And by analyzing this whole chain, we can finally and accurately predict what the signal looks like at any point along its journey.
Okay, so now we have this much more powerful model. What does it actually tell us about what happens to a signal as it travels? Well, it reveals that the signal changes in 2 really important ways as it moves down the line.
All of that wave behavior gets neatly packed into a single complex number. It's called the propagation constant, and we use the symbol gamma. Now, don't let the complex number part scare you. It just means it has 2 distinct parts: a real part, which we call alpha, and an imaginary part, beta.
So let's break those 2 down. Alpha is the attenuation constant. Just think of this as the fade factor. It tells you how quickly the signal's strength, or its amplitude, dies out as it travels. Then there's beta, the phase constant. This tells you how the wave's phase, kind of its position in its own cycle, gets shifted or delayed as it moves down the line. So now,
With these two tools, alpha and beta, we can really see the difference between a perfect, theoretical transmission line and the kind you'd actually use in the real world.
First, let's look at the ideal case, a lossless line. In this perfect world, the attenuation constant, alpha, is 0. There's no fading. And as you can see, as the wave travels, its amplitude, the height of its peaks, stays perfectly constant. It doesn't lose any strength at all.
And now, welcome to reality. This is a line with losses where alpha is greater than 0. The wave starts out nice and strong, but as it travels, its amplitude just shrinks, following this exponential decay. The signal gets weaker and weaker. This is exactly what happens in every real-world cable because of things like resistance. So all of these ideas come together in a handful of key equations. These are really the toolkit for analyzing any transmission line. Our 4 distributed parameters, R, L, C, and G, they're the building blocks. And with them, we can calculate everything else we need to know: how the signal changes, the inherent impedance of the line, the speed of the wave, and its wavelength. This table right here, this is your cheat sheet. It summarizes all those core relationships you'll need.
And that brings us to the end of our intro. We've gone from a simple little circuit all the way to a completely new way of thinking about how signals travel. So now I have a question for you. Once you start looking for it, where else do you see this theory in action? Think about the high-speed data zipping through a USB cable, the signal reaching your phone, or the countless connections inside your computer. Transmission line theory isn't some abstract concept. It is the fundamental physics that makes our high-speed, connected world possible.